My name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to talk about 1-3 reacting masses and volumes. This is going to be part 2 of the IB Chem SL curriculum. Let's get started with Avogadro's law. So equal volumes of gases when measured at the same temperature and pressure contain an equal number of particles. So it doesn't matter the identity of the gas. We have hydrogen, carbon dioxide, and nitrogen. And these are all at the same temperature and pressure with equal volumes. We're going to have the same number of particles of these gases in these containers. Let's talk about STP. STP, or standard temperature and pressure, is a little bit different in IB than other curriculums because the number of moles in a gas at STP is 22.7 instead of 22.4. That is because STP temperature is at 0 degrees Celsius rather than 25. STP pressure is going to be 100 kilopascals. So let's take a look at a problem. If we have 0.02 grams of helium at STP, what volume would it occupy? So we can convert grams to moles using the molar mass, which we find in the periodic table. And once we have moles, then we just use that. In 1 mole, there are 22.7 decimeters cubed volume of gas, and so we get 0.114 decimeters cubed. Units, here are just some of the units that we're going to be using throughout the gas laws. Okay, so ideal gas behavior. Move myself up here. When we are thinking of ideal gases, we describe them this way, that they are randomly moving particles with almost no volume. They cannot interact with other particles, so there are no interparticle forces, and when they collide, the collisions are perfectly elastic with each other as well as with the walls of the container. There's no such thing as an ideal gas in nature, but it's useful. So then why are we studying it? Well, it's useful to think a bit to be able to kind of predict under typical conditions how gases would behave. So here are some gas laws that you should know. We've got Boyle's law, which is pressure and volume, Charles' law, which is volume and temperature, and Gay-Lussac's law, which is pressure and temperature. And we can use those 3 gas laws to combine them to get the combined gas laws, which is P1 V1 over T1 equals P2 V2 over T2. So let's take a look at a problem. One of the animations didn't work, but let's take a look. So we have a molar volume of gas at STP is 22.7. Calculate the molar volume at 25 degrees at the same pressure. So since we're at the same pressure, the only things that are changing are volume and temperature. So we're going to be using this equation. Remember, let's convert our 25 degrees Celsius to Kelvin. So we're going to add 273, so 198 Kelvin. So V1 is 22.7. P1 is 173 because we are at STP, so we're going to use the STP temperature for P1. And we're bringing it up to 298. And we're going to look for V2. And so V2, if we do these calculations, you can just cross multiply and then divide by 273. We get 24.8 decimeters cubed. Ideal gas equation. So using the combined gas law and Avogadro's law, we can get this ideal gas equation, which is PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant. Now the gas constant is found in your data booklet, and T is the temperature. Couple of things about units. They must be in these units. So pressure must be in pascals. If it's in kilopascals, multiplied by 1,000. Volume must be in meters cubed. If it's decimeters, divide by 1,000. Centimeters, divide by 1,000,000. Temperature must be in Kelvin. If they give it to you in Celsius, add 273. And moles must be in moles. If it's grams, divide by the mole mass. The gas constant is 8.31 for joules over joules divided by Kelvin times moles. Now, you might be a little bit confused about where these joules are coming from. So the joules is just the pascal times the meter cubed. Gases behave like an ideal gas best when the pressure is low and the temperature is high. That's because if I have a high pressure, I'm squeezing those gas particles together. And when those gas particles are squeezed together, they have more chances of interacting with each other. Remember, an ideal gas does not have very strong interparticle forces. But if we're squeezing them together and we're forcing them to be in this kind of decreasing the space between them, then they're going to have more chances of having those interparticle forces. Same thing with lower temperatures. If we lower the temperature, we're lowering the kinetic energy. So usually these gas particles are moving by each other so quickly that they don't have time to interact. But when you cool down a gas, it starts to slow down. And when they're slowing down, then they have more time to kind of interact with each other. And therefore, they're going to deviate. Let's take a look at this problem. So calculate the volume that 0.02 moles of butane would occupy at 70 degrees and 1.10 times 10 to the 5th pascals. So we're going to use PV equals nRT. Our pressure's in pascals, that's good. Our volume, we're calculating that. Our N is in moles. We have our gas constant, T. T needs to be in Kelvin. So 70 C plus 273 should give us 343 Kelvin. And so from here, let's just plug into our equation. 1 times 10 to the 5th pascals. We're looking for our volume. Our moles are 0.02 moles times our gas constant. Again, you can find the gas constant in the data booklet. That's joules over Kelvin times moles. And our temperature in Kelvin is 343 Kelvin. So when we do all this math, my volume is going to come out to 0.000518. Okay? Units, the Kelvin will cancel out, the moles will cancel out. If you remember, joules is equal to pascals times meters cubed. And so when you divide this on that side, the pascals will cancel out, so the only thing you're left with is meters cubed. I've got 2 sig figs here, or it could be 1, it could be 2. So let's just do 2 sig figs. So this will be 5.2 times 10 to the, that'll be 1, 2, 3, 4, minus 4 meters cubed. Okay, so a sample of A, which is 0.23 grams, when vaporized had a volume of 0.0785 decimeters cubed at 95 degrees Celsius and 102 kilopascals. Determine the relative molecular mass of A. So let's figure out at these conditions how many moles of a gas we would have. So let's do PV equals nRT. A couple of things. So our volume is in 0.0785 decimeters cubed. This needs to be in meters. So we're going to divide by 1,000. And we get 0.12375 meters cubed. Our temperature, 95 Celsius. This needs to be in Kelvin. So that's 368 Kelvin. Our pressure, 102 kilopascals, needs to be in pascals. So we're going to times by 1,000, 102,000 pascals. So let's plug it into our equation. We've got 102,000 pascals times 785 meters cubed. This is equal to N, which is what we're searching for. The gas constant, which is 8.314 joules per mole times Kelvin, and times 368 Kelvin. Okay, the kelvins will cancel out, the pascals and the meters will cancel out with the joules, and we're left with moles. And if we do this math, the moles comes out to 0.0026 moles. Now, they give us the grams, so we know molar mass is equal to grams over moles. So, the molar mass should be grams over moles. And so the molar mass that we get is about 87.88 grams per mole. And then here's our answer, grams per mole. So the volume of an ideal gas at 27 degrees Celsius is increased from 3 to 6 decimeters cubed. At what temperature in Celsius will the gas have the original pressure? Okay, so P1 V1 over T1 equals P2 V2 over T2. So we want the original pressure, so the pressures are actually going to cancel out. So we're left with V1 T1 over T1 equals V2 over T2. A couple of things. Let's just do this. So the volumes are 3 and 6. We're trying to find out the second temperature. And let's just say we forget to convert this. Let's leave that at 27. So 27 times 6. This is 162 equals 3x. So x equals 54. That answer is there. So if you didn't convert that, the possibility of you getting wrong and thinking it's right is there. Let's see if you actually were able to convert this. So 27 plus 273 is 300. So that's 1800 equals 3x. So x is equal to 600. This answer is also there, but what you need to notice is they wanted the temperature in Celsius. So I actually need to subtract 273 from this number. And when I do that, I get the actual answer, which is C. So the IB is tricky because, Mr. IB, he's out to get you. All the mistakes that you can make, the choices are there, so you got to be careful. A 0.01 mole sample of barium nitrate was formed was heated until it had completely decomposed according to the equation. Use the ideal gas equation, calculate total volume in centimeters cubed of gaseous products obtained at 387 Kelvin and 1.12 times 10 to the 5th Pascal. So we have 0.01 moles of barium nitrate here. And we want to know how many gaseous products. So if we look at our balanced chemical equation, we have two gaseous products. We have oxygen and nitrogen dioxide there. So if we do this mole ratio, we have 2 moles of barium nitrate for every, there's 4 and there's 1 here. I'm just going to put 5 moles of gas product. Okay, and when I do this, I get 0.025 moles. So now that I have my moles, I can use PV equals nRT to find out the volume. So my pressure is in 1.12 times 10 to the 5th pascals. I'm looking for my volume. I have 0.025 moles, which I calculated here. 8.314 joules per moles times Kelvin. And my temperature is already in Kelvin, 387 Kelvin. When I do these calculations, I get 0.000718 meters cubed. They want it in centimeters cubed, so we need to multiply by 1,000,000. So this will be 718 centimeters cubed.